Good Monday to you. Yeah, another week in paradise. Yes. How did it go with the lab? But you managed it?
Yeah.
Okay, good. So now Mons will collect all the responses and process it with our checker. Yeah, so let's see. But so next week, so lab two is built upon the results of lab one. So you will implement the reasoner itself. So it'll be fun. And then again, just to give you a pre-taste of what is happening. So now we are still, or lab-wise, we are still in the module of standard logics and the reasoning to standard logics. But already tomorrow, we will focus on a modern way of representing knowledge and reasoning upon this knowledge. So we will be talking about semantic web technology starting from tomorrow, ontologies, resource description framework. And lab three is in a way detached from first two labs. So it will be about something different. So it will be about knowledge representation and the new thing for this year, and I will tell more about it. I am introduce a new task where you will implement your own reasoner in a special way. So we will be talking in the next module, so in 2 weeks from now, about something which is called neurosymbolic reasoning. So that's what we do now. So that this logic stuff, it is in the core of something which normally is called old good-fashioned AI or symbolic AI. AI which is based on rules and formal logic. But as you know, nowadays when people talk about AI, so people most likely mean deep learning, and deep learning is about neural networks. Again, so I will not elaborate more on that now. So the question is, what is AI indeed? And the true artificial intelligence. So now it looks like researchers are converging to something which is called neurosymbolic way. So that these two worlds, where on the one hand you have neural networks and symbolic reasoning, symbolic knowledge representations, they converge. And in this lab three, I want you to try one of the such approaches. So you will read the paper. So I will publish it in advance. We will talk about it. I scheduled the class, so I will explain what is going on there, and then you will try it in the lab alongside with standard tools for reasoning on ontologies. Yes, but again, so we had this gap, practical gap between the classes. So I want you to remind me, what did we talk about last time we saw each other? Hmm? So what was it? Yes. So what was it on the last page? So what did we talk about?
Knowledge-based.
But more specifically, huh? Yeah, well, but we talked about logic, right? So we talked about um, simplest of its kind, which is called predicate logic. But so predicate logic, along with a couple of more advanced logics, belong to a class, something which is called standard logics. So let us see this taxonomy. So last time we talked about propositional logic. Or, and what is the main characteristic of it? So what can it do? Uh, what it cannot do? No, no, moments like this. Okay, so propositional logic. How do we describe facts? What are the facts? How did we describe the world? We have very, very simplistic view on the world. So out of all its complexity, we kind of, or we boil down all the complexity to logical variables, right? So we assign variables which can be true or false to facts about the world. So, false variables. And then we have predicates. So basically how these variables relate to each other. And in this way, we describe certain facts or certain observations about the world. But the world is more complex than that, as you than logical variables. So now I want you to think about uh, separation into two uh, domains, so to say. One is our physical world, with all the objects we have around us. So, for example, I see it in front of desk. So we have a desk. And I have a computer on a desk. So or later on I use table, so let it be table. Table PC. Uh, that that is obviously is kind of placed on the. I mean, it stands on an object we call floor. Then we have something else on the floor. I don't know. So I think. Cable case casing on the floor. So so these things, they're not logical, so they're physical. And somehow we want to reason, we want a machine or a computer to reason about them, to describe these physical objects and not only objects, but even the relations on them, how they relate to each other. So what we want, that I mean, from the AI perspective, or AI lives in a logical world. So, and again, so in the logical world, everything is about true or false. variable. So that how we want it. So essentially, we want somehow a function that maps objects from the physical world or entities and the relationships onto a logical world. And this function, so this function, which is from domain of physical world to the main to actually to truth values. So everything, the objects themselves and the relations, so we want to map them to the logical world. So this function is called a predicate. So predicate. I mean, on the one hand, it is a symbol. So, a symbol that takes a logical value. But it is a function in the first place. So, for example, example of predicate would be on. So we define it. We define it as we like. On. So let me just put it here. Example. On object table. Object or entity. So it is we who define it, but the meaning is that this function, it takes a Boolean value, true or false, and it maps from the domain of physical objects into our logical stuff. So, in essence, we describe sets of objects. I mean, via a predicate. So we collectively describe set of physical objects and their relations. In other words, so we operate on sets. But then we want also to make our logic more expressive. So we want to say that we want to maybe exclude certain objects, or we want to generalize and say that, I mean, this predicate, this function is applicable to all objects of certain kind. So in other words, we want to quantify which objects we mean, which objects out of a whole set we mean to be described by a particular predicate. And altogether, so the predicate that maps, the predicate set of predicates that we invent that map physical objects into logical variables, and the quantifiers that allow us to focus on specific groups of objects. So this define a more complex kind of standard logics, which is called first order logic. Indicates and quantifiers. So what we can do with these two things, predicates and quantifiers, we can describe structured facts. So now we introduce not only the objects being true or false, but we also introduce structure. So how these objects relate to each other, and even and rules. So first order logic is the foundation of, as I said, of a classical or AI in its classical definition, symbolic AI, and as well as many useful technologies which we normally do not connect to AIs, like databases or ontologies that we will be talking about in the next module. So let us focus on first order logics, and just on a simple, or maybe simple but still a little bit mind-bending example. So as you can imagine, so one can spend half of a course talking about different aspects of first order logic. So, but in this context of this course, I just want to give you a slice of it. So let us focus on this predicate and formally introduce quantifiers. So, for example, on table object on table. Or sorry, but I'm just our predicate is on like this. So and so it takes values true or false. So this could be a variable, and this can either be a constant or a variable. So let us introduce quantifiers, and again, maybe the most important relation. So we have in first order logic we have two quantifiers. One which is called the universal quantifier, and another one which is called existential. So universal is denoted like this. So you remember probably from your previous courses. Sometimes syntactically you can put colon. In some cases you can omit colons. And the translation is like for every for. And existential is denoted like this. Remember, so, and again, the linguistic variant is there exist. So the major relation here is looks like this: not for all or for every variable, some formula, a predicate of this variable. So which this is logically equivalent to there exist object such that not this formula or this variable. So as an example, I suggest you to think about the following. So let me just not all I on. So we continue our table example. Table implies there exists J. So now we have another item on J floor and not touch IJ. So what I want you to do now to make sense of this formula, of the relation encoded in the first order logic syntax. So this is syntactically correct sentence. So no problems with what the syntax is here. I want you to parse it somehow and tell me, so what holds for any item on the floor or every item, every. So you see that it's a very, well, it's a rather complex sentence. So which describes the relations of items. Some items are on table, some items on floor, and some items interact. So they via touch predicates. So the task is to interpret what holds for all items, every item placed on the floor in this sentence. And So I give you a couple of minutes again, just to maybe to chew on it and develop a strategy. So I don't ask you for a solution immediately. I just want a strategy. In Zoom, you also can unmute yourself and speak up, so, or maybe to write in chat. So I will look into chat. I will remain closer to the mics. So I also expect some ideas from Zoom listeners on strategies, how to attack, how to approach solving this problem.
Nej, då brukar vi ha hela klimatprogrammet. Då tänker jag att man använder ju det som var teori. Man har inte samma grej. Det är en central musik. Okej. Jaha, om det har det så. Eller det är liksom, där är som när vi var intresserade. Implies att det finns
A hint, when you see such kind of problem, don't try to make it as a mental exercise. So always, so this is about logical inference, applying rules, major rules. I mean, we covered some of them last time, you know, this De Morgan rule and such. And so here, I just want to probably to put to draw your attention again to this rule over here. So for starters, again, so this is a made-up example, of course, but this is something to complex to complex to interpret directly. So not for all and then something. So we need to do some simplification. And in what followed, but maybe that was a task to you. So what is the approach? So how would you approach solving it? First question, this quantifier, first quantifier for all I, to which part of the formula it is applicable? Huh? No. It is applicable to everything that contains I. So essentially, this quantifier works on the whole formula. So this is a formula for this quantifier because it it contains I here. So I here, I there. Okay. So to begin with. And so now we want probably to turn it to something more interpretable, so not for all. So then again, we can turn it into an existential.
I'm sorry, could you remove the chat?
Yeah, sure, of course. Turn not I into existential. Just to remind me, so this is this formula over here, so which is logically equivalent to there exists an object, and we negate the formula. There exist objects such that, and we negate a formula or the sentence, if you wish. I. So, which is there exists. Oh, sorry. Why all? It should be I, of course. There exists I such that not, and then just to maybe for clarity of calculation. So in this formula, so this is an implication, right? So something implies something. So let's say so this so denote as x, and this thing over here as y. So, and I skip the argument. So properly it would be x of I and y of I and j with some constants in it. But so just treat them as simple logical variables. So not, and then our stuff not x implies y. So that's something already simpler. So, but we are not there yet. So we eliminate implication. So that stuff over here results into not x and or sorry, or y. You agree with me on this one? So that's maybe I should put where do I have it? Maybe somewhere here. Table here. Um, no, and I make it smaller, and a little bit smaller. So now we see everything. So like this. So what we applied elimination of implication. So not alpha or beta. Next, so so this is equivalent to obviously X and not Y. So where is the corresponding rule? Yeah, De Morgan. So the added De Morgan, so the third from the bottom. You negate both and you change the logical operation. So maybe at this point I want to remind you that this X is on I table, and this Y is what is it? It's all this thing over here. So see next page. So Y is our what is it? Or not Y. Y is not, and then so all this stuff which is, well, I don't need actually this exist J such that on J floor and not touch I J. And again, this existential quantifier, it is applicable to the whole thing. Keep on thinking. So that's the homework for tomorrow. So I will start with it tomorrow. But so far up to here, everything is correct. So now we need to straighten the last bit. So we come back to this example tomorrow. To get stuck. Yes. But for today, so I want to give you an overview of something different. So far we talked about standard logics, so predicate and first order logic, which describes the facts and relations between the facts. Can you reconfirm what do you see in Zoom? So do you see me in presenter mode or?
Right now, we just see your desktop.
And what about now?
Now we see it full screen on the slide.
That's good. So we talked about describing the world, the facts and the relations between the world as logical variables and applying logical rules for inference. The special assumptions we had about variables, so that they are exact, so the facts are described in an exact manner. So what about a situation when we want to introduce some uncertainty. For example, you want to describe a system using some, well, let's use this word fuzzy terms. So you want to interact with the system linguistically. So if dishes are dirty, use hot or hotter water than usual. If there are many dishes, use more water. So, and the question is how to deal with such variables. Hotter, dirty, many. So we need to quantify them somehow. So a simple example. So if I ask you how many years is old, so notion of old. So let's make a poll. So what are the, so we are not that many here, but it's still quite representative. So how old is old for you? Just shoot. Huh?
80.
The one number. 80.
70.
70. 73. 70.
75.
You're also 70.
70. Yes. What about you? How old is old for you? Yes. How old is old for you? Okay. Yeah. So what was it? So we have some average, right? And some span of values. So that remember this. But what did I do now? So I mean, I give you an example of kind of really asking experts, domain experts, about given assessment of certain phenomenon. Why do we why do we want such kind of fuzzy definitions? Well, simply because truth values they are not always applicable in real world. So if you think about the following rule. So in standard logic, so you need to be very precise. So you have a variable for pressure, you have a notion for degrees centigrade or well, bars for pressure, centigrades for temperature, and you construct these rules. However, in real systems, all these quantities are measured by sensors, and they are not precise in general. So they give you value in certain span. So that's one of the reasons. Then again, so human interact with the systems, and they can give very vague assessment of certain phenomena. So we need ways to account for this imprecise definition. So we want to basically treat formally a linguistic way of specifying rules. So if pressure is higher than usual and temperature is extremely high, then do something. So and the part of logic that deals with this kind of uncertain definitions is called fuzzy logic. It is used, is found lots of application in automatic control. So whenever you cannot describe a system with formal model, so the dynamics of system with the formal model, then fuzzy logic will help you with this. So to introduce you to fuzzy logic, so we need to first define what a linguistic variable is. And linguistic variable we will use to transform expert knowledge into concepts with this fuzzy logic. And then we will have a fuzzy set. So we will define these variables formally, and a specific phenomenon will be a collection of fuzzy sets. So in addition to membership to linguistic variables, so we want to introduce a membership function, a function that describes a judgment about a certain linguistic variable. So, for example, if we have fruits as an object, and we want and a variable describing the quality of this fruit would be tastiness or ripeness. So we somehow want to quantify, give some numerical incarnation of this variables. And for this, we will use something which is called a membership function. And the membership function is a mapping of expert opinion into a single value. Normally, it is not normally, but it's a requirement that it is bounded by between 0 and 1. What we did previously, when I asked you about the years to be qualified as old, so I just collected scores from experts. But now you want to collectively describe the scores using a single function, where you would enter a score as an argument, and you will get a value as an output. So whether certain score belongs to a definition of a linguistic variable. So some examples, simple examples. So we work with fruits. Fruits can be unripe, ripe, and overripe. So you ask 100 people, you give a scale from. So you define a scale between 0 and 100, say, or whatever. So on axis, and then you ask people to score certain categories of fruits. And define the range which correspond to ripe. And it happens that during this process, so the distribution look like this, that up to a certain score, so people definitely said it is ripe, so the value is 1, and then as exactly as in our case, so you have somebody who thought that the border of all this longer than others, and this is reflected in the shape of the function. And the same goes for ripeness. So if we have our linguistic variable ripeness or ripe, so then the membership function may look like this. And correspondingly, so we can do the same for overripe. So that is more of a step function, because beyond certain limit that everybody agrees that it is the fruit is overripe or bad. And again, so far we talked about collecting the scores. So all these functions here you can express mathematically, obviously. And there are different shapes of this function. So the choice of membership function really depends on a case. So normally you can try different. So you look at the responses of scores, and then you try to fit probably certain distributions of how it looks. And then you can approximate this distribution. So at the end, it is the designer of the fuzzy logic that chooses a specific membership function. Here I include a couple of links, so they will be available in the PDF with very good tutorial and code snippets to work with fuzzy logic. But the idea here is to introduce the overall principles. So now what we did, we defined linguistic variables, so something we want to include in our reasoning, and we defined the membership function, so something that gives concrete value to a range of scores in this in the domain of this linguistic term. And as I said, certain concepts can be described by collection of membership functions. So exactly as in the case with rightness, you can define, for example, or a set of membership function for a range of values. Values of concrete measurement phenomena, measured phenomena, for example, a voltage. But you define it in positive terms like medium positive, for example, large positive, medium negative, large negative, or centered around 0. So what do we want at the end? So we want to have a freedom to not being exact in our reasoning. So we can say, so when constructing rules, we can say not that voltage should be above 5 volts, but rather we may say that in certain situations we can treat it as large positive, or in certain situations as medium positive. So depending on what rules we have. And then when we have a fuzzy set, so basically a collection of variables along with membership functions, we can combine them. So pretty much as we did with standard logics. There are other ways exist, but I mean, so these are examples. So if you simple examples come up with the direct link to standard logics. So you have a membership function. So it is bounded between 0 and 1. So negating this values, this variable would result in membership function 1 minus membership function of the variable. All in all, so we want to create a system that reasons. So we will have a knowledge base that contains rules using our linguistic variables. So the system will take as input precise measurements. So the measurements from the sensory systems, and then map it to the fuzzy sets that we have defined by asking our experts. And then the reasoning will be applying all rules from the knowledge base in which this linguistic variable appears. And then at the end, I will show you an example later. So you need to convert, so the result of this reasoning, again, should be a precise value. So the knowledge base, as I mentioned, will contain the fuzzy sets, the description of domain values, and rules describing what to do with them. So here is an example of the simple rules applicable to our fruits example. So if so we want to make a system that takes a score of ripeness of apple and decide what to do with it. So we have maybe even an automatic system that determines gives a value of ripeness. So the decision is like this. So if apples are overripe, so good for cider. If apples just very good, so then it's good for juice, and otherwise for chutney. So the first step, before we do, we can apply this rule. So these rules are stored in the data in the knowledge base. Before we can apply them, we need to fuzzify the concrete measurements. So we have different functions. So we have different linguistic variables and different membership functions, and all of them are activated during the measurement. So you take particular apples and you try to compute a score of all membership functions that deal with different linguistic variables. So at the end, you have a vector of linguistic variables, and so the measurement system reports your concrete outcome. So that's it is definitely not unripe. It's so for this particular score, so membership function tells that it's 20% ripe and 80% overripe. So this value now is given to you by the measurement system. The functions are kept in the memory. So you apply this this score to all the functions you have, and so all the functions are they're visible in this vector of values, and that is your fuzzy variable for the quality of this particular set of apples. So now, remember that here is our very simple knowledge base with all the rules applicable to, in a given scenario, so for producing these three products. So in fuzzy logic, all rules apply simultaneously where you for a given linguistic variable. So what does it mean? So you pick up all the relevant rules from the knowledge base, and apparently, I mean, in this example, all of them are applicable. And then you apply them to the degree indicated by your fuzzy variable. So 80% of the rule will be of the first rule, so 20% of the second rule, and 0% of the third rule. So essentially, the result of the reasoning is also a fuzzy variable. So something that okay, so maybe you do some a certain percent you do cider, a certain percentage you would go for juice. So, but you need a single answer from the system. And that is done by a block which is called defuzzifier. So the defuzzification happens in pretty much similar manner. So let me see if I, yeah, that will come later on. So you have membership functions even for the rules. So it's part of the knowledge base, which gives you the interval of values when this rule is activated to a certain yeah. So for a given value, like, well, somehow it was shifted. Let me. It should be somewhere here, I guess. So when you scan your knowledge base and apply all the rules, so you see you get the fuzzy output variable. So and how do you work with it? So you take all the membership functions for different products that you have, and now you need to collectively represent the area, the intersection of these membership functions, which looks pretty much like this. So then there are different ways on how to compute one specific outcome. So you can take a minimum value, for example, of this intersection, or maximum. So in this very case, you would compute a centroid, so a central value, and output the score as something what is called the crisp output. So that will be your final decision. Yes. Right. So what did we do here? So we defined the system which works on not on crisp values, but rather on opinions from experts. But and for this we needed to quantify these opinions, and we do it by assigning membership functions to linguistic variables that we ask opinion for. The same we do for output values. So in this case, it was a profit that a company gets when producing different values. And the idea is to decide. So the goal with the reasoning is to decide which product is best to produce with a current batch of fruits to maximize a profit. And that we did by applying all the relevant rules with the scores reported by the membership function, and then collectively deciding deciding on the output, analyzing the intersection of the sets of outputs like this. Well, I think the time is out, so I will present another example tomorrow, and then I will come back to the first order logic example as well in the beginning of the class. All right.
Thank you.
Thank you.